The previous case, the first and the last speaker are not here, so I'm trying to uh, represent their work. I think everybody saw, probably most people have seen some astonishing work coming out of the large international group that showed that you can take chest X-rays and predict with extremely high degree of accuracy what self-reported race is. And as I noted in that paper, despite a lot of different experiments, they were not able to quite figure out exactly what the network was looking at in order to be able to do this task so well. They looked at a variety of experiments, they looked at different filters and different resolutions, but the performance of the network in being able to classify self-reported race from X-rays was extraordinarily high. So I think the goal of this work was to essentially come up with a method to highlight the areas in which may be relevant to the task of race prediction. So as mentioned, the first reference here showed that self-reported race can be predicted really well, even though most clinicians cannot do it and cannot really say what they think the race-related features are. There's also been a lot of work, again, as you've seen a lot in this workshop, where some of these models are quite biased with respect to patients' race, and so the ability of the models to very easily pick up race is something that one should be concerned about. There's also threats to privacy because we've shown in both in test X-rays and other things that you can predict a lot of things about a person from that image. Right? You can take someone's fundus photograph and say how old they are, whether they're a smoker, what their risk of cardiovascular diseases. So there's a lot more information encoded in images than we typically tend to think. And so this is again potentially a threat to privacy. There's been a number of approaches in terms of interpretability to try to look at these features and try to visualize that. And very few of them have really sort of succeeded in figuring out what exactly is might be the part of the image that drives this ability. Occlusion maps are what have been reported previously, where they again have used those to say, okay, if I occlude out this part of the image and there's a classification change, and perhaps that means that that part of the image is relevant to the task. So the work in this work, the goal was to essentially create a Cycle-GAN. So start off with the assumption that we have a really good self-reported race prediction classifier. We are now trying to figure out what is it about the image that makes the network able to do that task well. So we train a Cycle-GAN to essentially transform race. So take a patient who's like you transform horses to zebras, you take a patient whose self-reported race is white and you transform it to black. And so and the ability to do that. And the way we work, we can make sure that that is somewhat working correctly, is that then you take that transformed image and run it back to the race classifier. And if it does a good job in saying, okay, the race is now black, and when the original image is white, then perhaps the Cycle-GAN can do its job in terms of doing this transformation. And once you've done that task, then you look at pixel-wise differences. And hopefully that provides some insight into the parts of the image that might be relevant to the race classification task. So in the first row, you can see that we took a patient of one with self-reported race, ran it to the Cycle-GAN, transformed it, and looked at the pixel-wise differences, and the areas that lit up were the ones that were highlighted in the same sort of thing in the other case. So the data set used for this was MIMIC, and the training validation methods are given there. It is a fairly standard model that was used to predict race. Again, performance is really good. And then they compute so you take the cases where the race was predicted. So after the transformation, the race flipped, and looked at those images where that Cycle-GAN was successfully able to fool the classification network, and then look at the differences between the pixels on a pixel level between the two. And then we also compare that to sort of standard occlusion maps. and then looked at differences based on, are there any differences based on gender. So the inclusion maps are not very informative. So again, sort of looking at the idea of the inclusion map, again, you patch out, maps out patches of the image and run it through the classifier, the race prediction classifier, and if it flips its prediction that means those regions are important to the task, and they're not super informative, but you can see the areas that will let up. In the way that the authors do the work here, they looked at the Cycle-GAN and looked at the. So if you took the cases where the Cycle-GAN was very able to successfully fool the race classification network with high degree of probability. So if you look at the leftmost column, the score of the race prediction classifier is very high. So take those images, compare the original true image with the transformed image, and looked at a pixel-wise difference and sort of average that over all of the images in the test set. You can sort of see the areas that seem to be relevant to this race classification task. And you can look at them in both directions. Again, looking at by gender, there's not a whole lot of difference, very similar looking maps. Some differences, in a lot of cases, the sort of the neck and clavicle area seems to be lit up and so on. So in conclusion, the authors were trying to address the issue of trying to figure out a good way of finding an interpretability method to figure out which part of the image is relevant to the task of classifying race, self-reported race from chest X-rays, looking at different pixel-wise difference maps between an image and a Cycle-GAN transfer generated version of a flipped image seem to suggest some areas that might be of importance. And again, those areas seem somewhat consistent, but then across all of these images, an average map highlighted quite substantial areas. And so the question is potentially why? And that we obviously do not have any answers for. And then there are differences between male and female was not substantial. They basically highlighted the same sort of areas. And so lots of ways in which we could take this work further, but the idea of sort of training this Cycle-GAN seems to be a limitation in the sense that we have to train a Cycle-GAN, we make sure it's working correctly, and then we only looked at one task, which is this particular self-reported race task. We want to know what we can do with other tasks as well. And we also just looked at this mimic data set. So we have plans to look at other public and private data. Thank you.
Here is different because the region alone doesn't have that.
No, exactly. No, we have not done that yet. And then that's very much sort of, and we really need to talk to like an X-ray, like a physicist to understand is there what potentially differences are there in the settings of the image in the acquisition protocol that might lead to such differences, but no, that's something we'd be very curious to explore further. So we have not done that.